In this lesson, we're going to learn about how to find the volume of cylinders. So the volume of a cylinder is found by multiplying the area of the circular base by the height of the cylinder. So what that really looks like is the volume is the area of the base times the height, or the volume equals capital B times H, which is the same as what you saw for volume of prisms. The only difference is, since we're talking about cylinders, cylinders always have circular bases. So that means the area of their base will always be the same since we're talking about circles. So really the easiest way to remember the volume of a cylinder is by using this formula here. Pi r squared, which is the area of the base since it's a circle, times the height, times the distance between the two bases. So the height is always going to be that perpendicular distance between the bases. And then the area of your circle, this will always be pi r squared. So we're going to multiply those. The area of the base times the height, and that'll give us the volume. So if we look at this first example, find the exact volume. So what this means when it says exact volume, it means no rounding, so no decimals unless they're decimals that end, which really means in terms of volume that we're going to leave in terms of pi. Because since pi is irrational, if you were to put pi into your calculator, it's going to make your value not an exact value. So we're going to leave it in terms of pi. So we want to find the exact volume of a cylinder whose diameter is 18 inches and whose height is 2 feet. So the first thing I want to do is I'm going to draw a picture of my cylinder here. And I know that the diameter, so that means the entire length across is 18 inches. And the height is 2 feet. Now, right away, I'm noticing that my units are different. And since my answer or my question here doesn't say what I need to find the volume in, it doesn't say if it has to be in cubic inches or cubic feet, I can pick which unit I want to convert. But what I do need to do is make sure that these are in the same unit. So I'm going to go ahead and convert the 2 feet just into inches. I think that's a little bit easier. So 2 times 12 is going to give me 24 inches. And that's what I'm going to use. So I'm going to make my answer in cubic inches. So when I write my formula, volume equals, I can write capital B times H, use the prism formula, and then just substitute in that circular base. But I'm going to go right ahead and just write pi r squared times H, because that's the formula you're always going to use for cylinders. And then I'm going to go ahead and plug in. So I have pi. Well, if the diameter is 18, that means that the radius is really 9 inches, since it has to be half of the diameter. So now I'm going to plug in 9 squared times the height, which is 24. So in order to make this happen, in order to leave this in terms of pi, I'm going to enter everything into the calculator except for pi. So what I'm entering in is 9 squared times 24, and that's giving me 1,944, and I need to keep the pi or carry down the pi. So 1,944 pi, or times pi, inches cubed, since I'm in inches. So that would be my answer for that one. And again, if I were to turn this over into feet, that's fine. But you were going to end up with a fraction, and I felt like going to inches was a little bit easier because then it's just times 12. Okay, we'll talk more about unit conversions after, but it's very important that your answer has the correct units on it, especially because we started with 2 different sets of units in the problem. So now, if we look at this next example, a cylinder has a volume of 1,470.27 cubic feet. If the height of the cylinder is 13 feet, find to the nearest inch. Okay, look again, we have a unit conversion. That's a red flag. The length of the diameter. So what I'm going to do is I'm going to find, since this is in cubic feet and this is in feet, let's do everything in terms of feet, and then when we're all done, we'll just convert it over to inches. So we have a cylinder that has a volume of, so let's go ahead and just draw a picture here. Not drawn to scale, but I'm going to say that the volume of this is 1,470.27 feet cubed. Again, keeping track of the units is so important because of these unit conversions. The height is 13 feet, so making sure we're labeling with our units. We want to find the diameter. I want to find that entire thing. So let's go ahead and write our formula. So pi r squared times h. I'm going to plug in what I know. So 1470.27 equals pi, the radius I don't know, times the height. And since we are going to be rounding to the nearest inch, I'm going to go ahead and actually divide out the pi. So meaning I'm going to put that in my calculator, but I'm not going to round my final until I get to the final step. So I'm not going to round until it's my final answer. So what we need to do here is we need to get the r by itself. This is where you have to be careful in your calculator because unless you specify, because I want to divide by 13 pi, in my calculator, if I just go ahead and say 1470.27 divided by 13 pi, your calculator won't know that you want the 13 pi to go on the in the denominator. So you need to either put parentheses if you're just using the division symbol, or what you need to use is the control divide and actually set up a fraction and make sure that it looks just like this. Because otherwise your calculator will want to divide by 13 and then multiply by pi. So you need to specify, no, I want to divide by that entire thing. So 1470.27 divided by 13 pi, I'm using the pi key, and I'm getting 36.0001 equals r squared. Now to solve for r, I'm going to square root both sides, and I'm going to use the exact value from my calculator. So I'm going to go ahead, arrow up, use that entire decimal, and I'm getting 6.000401. And technically it's plus or minus because we square rooted a variable that was squared, but since it's a radius, I need it to be just a positive. And then I want to think about my units. I dropped my units when I put it into the formula, but I want to make sure I know the units now. You could write them in the formula as well. Sometimes I think it gets a little confusing, but sometimes it's helpful too, so you see them along the way. But I know that this is in feet. So that would tell me that the diameter would have to be 2 of those. So I'm just going to say times 2. And again, I'm using that exact value. I'm not rounding here. So I'm getting 12.00000189 feet. I want to make this into inches now. So if it's 12 point, so let's just say approximately 12 feet, I want to convert it over to inches. So let's just do that right up here. So I'm going to say the diameter. So to convert that into inches, that means it has to get smaller. So we're going to, let's go ahead and just do our conversion. So 1 foot is equal to 12 inches. So 12 inches is on top, 1 foot is on the bottom. So you're going to multiply that by 12. So there's going to be more inches. So times 12. And we end up with 144 because the feet cancel here. So 144 inches is what we're rounding to. So I'm just going to write it up top here because it's like 144.000227. So I'm just going to say 144 inches would be my final answer. And then the last thing that we're going to look at here is something called Cavalieri's principle. And I'm going to make this an A. It should be an A for Cavalieri. And it's basically, it's almost like common sense in a way because what it's saying is if you have, if two figures have the same height, so let me just kind of box in these important words, the same height and the same cross-sectional area at every level, then they must have the same volume, which makes perfect sense because if you think about the volume formula for prisms and for cylinders, the area of the bases times the height is equal to the volume. So what this is saying is the same cross-sectional area. So basically the area of the base, if it's the same for every prism, and if the height's the same for those prisms, well, then the volumes have to be the same, which makes perfect sense because if you plug in the same number for the area and the same number for the height, well, then you're going to multiply and you're going to get the same number. So if you look at these examples, if I were to find the area of the base in this rectangular prism, it would be 3 times 2. And then the height we're saying is the same. And then in this one, this is an oblique prism. It's slanted, but the formula for this it's a parallelogram, will still be the same, 3 times 2, base times height. And then this triangular prism, it would be 1/2 base times height. So in the end, 1/2 base 6 times the height, which is 2, is going to be the same thing as saying 3 times 2. So it'll still end up being exactly the same. And then we'll say that these heights are all equal. So then therefore, these would all have the same volume, even though they are much different looking prisms. So they would have to have the same volume. And actually here it says right here that they have the same height, and then the area is the same at each section, or the bases are the same, so then each section is the same. So that's Cavalieri's principle. It's basically saying if you plug the same thing into the formula, well, they're going to be equal. So here's an example from the state, a sample problem. So it tells us that we have 2 stacks of 23 quarters. One stack forms a cylinder, but the other stack does not form a cylinder. Use Cavalieri's principle to explain why the volumes of these 2 stacks of quarters are equal. So in this situation, we have to think about Cavalieri's principle, which means we have to talk about the areas of their bases at each level and the heights. Therefore, the volumes will be the same. So you have to mention those things in order for you to be able to use Cavalieri's. I'm noticing that Cavalieri's is spelled wrong multiple times here too. Maybe there is another spelling of it, but the one that I just saw was with the A. So if we look at this, let's talk about the heights first. There's 23 quarters in each of these. So if there's 23 quarters in each, well, then that means that the heights are going to be the same, because each quarter is going to have the same thickness or the same height. And if there's 23 of them, well, overall the heights will be the same. So the first thing here I'm going to say is there's the same number of quarters in each stack. So this implies that we have the same height. So that's the first part of Cavalieri's. We have to have the same height. The second part is we have to talk about the area of the bases at each cross-sectional level. So no matter where I take a cross-section, I'm going to have the same area. So if we look, since these are all made up of quarters, well, the area of the base of a quarter is going to always be the same. So I'm going to say that it's the same area for each quarter. So this implies that we have the same cross-sectional area at every level. So this is the second part to Cavalieri's. So now I can say that, therefore, the volumes must be the same by Cavalieri's principle. So this implies, therefore, by Cavalieri's principle, the volumes of both stacks are equal. And it's because I mentioned same height, same cross-sectional area at every level. All right, so go ahead and write some key ideas down from this video and then try the check your understanding problems. And like I said, we'll talk more about these problems in class tomorrow, as well as talk a little bit more about unit conversions in class.